In this discussion video, we'll talk about how to handle indeterminate forms of the type 1 to the infinity, 0 to the 0, or infinity to the 0. So the things that have these exponent forms. We'll do some examples of these. So I want to look at first problem number 15 from worksheet 10. It's the limit as x approaches 0 from the right of x to the sine x power. So before I give you a chance to try this, I want to just plug in and see what I get. So if I do that, if I plug in, I'll get 0. If I just plug in straight up 0, I'll get 0 as a base. And then to the sine of 0 power, which is 0. So I have 0 to the 0. And I briefly want to talk about, well, why is something like this indeterminate? So in general, if I have 0 as the base, and I have an exponent, which I'll call a, this is going to be 0 as long as that exponent is positive. So 0 to the a is 0 typically, as long as that exponent is positive. Okay, whereas if I have some other number in my base and my exponent is 0, this is 1, as long as that base is not equal to 0. Okay, so what's going on is, seeing that the base, because we're taking a limit, the base is getting really close to 0. Seeing that the base is getting really close to 0 makes me think that the whole thing should just be 0, as long as the exponent is positive. And in this case, the exponent will be positive because x is approaching 0 from the right-hand side. That's going to make the sign be positive. But on the other hand, when my exponent is 0 and the base is non-zero, that the whole thing should be 1. So it's sort of like, what dominates? Is the 0 on the base dominating, or is the 0 on the exponent dominating? That's going to affect, will this whole thing be 0, or will it be 1, or will it be tugged somewhere like in between the two? Okay, so that's sort of a conceptual reason for why it's indeterminate. There's sort of two conflicting things happening. Okay, so now I want to give you 5 minutes to try this. 4, 3, 2, 1, pause it and try it for 5 minutes. All right, let's talk about it together now. So recall that our strategy for these is to first let the whole limit be equal to some new variable. I'm going to call it y. So let y be the limit as x goes to 0 from the right of x to the sine x. Ooh, x to the sine x. And then what I do is I'm going to take ln of both sides. So ln of the left and ln of the right. So we'll have ln of y equals ln of this limit as x goes to 0 from the right of x to the sine x power. Because what I can do now is, I'm going to start to simplify what I have on the right-hand side here. I'm going to pull the limit in front and get the limit as x approaches 0 from the right, and then of ln of x to the sine x. So I can move the limit in front since the function I just pulled it out of, the ln function, ln of x, is continuous. And when that function is continuous, we can move the limit in front of it or outside it. Okay, because now the nice thing that happens is we get this limit as x approaches 0 from the right, but I have ln of something to a power. So I can pull that power in front of the ln. I get sine x times ln of x. And now the exponent part is gone, or at least we've moved the exponent using this log property. And if we plug into this, we'll get sine of 0, which is 0, and then times ln of, and the inside of ln is getting close to 0 from the right. That'll mean that goes to negative infinity. Okay, and we've seen indeterminate forms like this before, 0 times infinity or 0 times negative infinity. We handle those by rewriting what we have as a fraction, and then we'll check to see if our fraction has the form 0 over 0 or infinity over infinity, so I can do L'Hopital's on it. Alrighty, so we'll get the limit as x approaches 0 from the right. So when I rewrite it as a fraction, I gotta choose one of these terms, either sine x or ln of x, to move to the denominator, and when I do, I have to reciprocal it. And usually I pick whichever is easier to reciprocal, it just looks easiest to. So here, I'm going to move the sine x to the bottom. I'll keep ln of x on top. So on the bottom, I'll get 1 over sine x, because I know what 1 over sine x is. That's going to be cosecant x. This is cosecant x. Okay, and if I try plugging into this now, the numerator is negative infinity, And the bottom, 1 over sine x, that's going to be 1 over, and the sine is getting close to 0. But because x is approaching 0 from the right, that means my angle is a little bit bigger than 0. And if it's a little bit bigger than 0, that's like in the unit circle, we'd be somewhere over here, getting really, really close to 0, but we're a little bit bigger than it. And on that side, sine is going to be a little positive. It's going to be a little bit bigger than 0. So I'll put a little plus sign here. So this whole thing equals negative infinity over, and the denominator is positive infinity. This is now something I can do L'Hopital's on. All right, so I'll write equals, I'll put LH, we're going to use L'Hopital's. We'll get the limit as x approaches 0 from the right. And then I do the derivative of the top first, which is 1 over x. On the bottom, I'll do the derivative of cosecant x, which is negative cosecant x times cotangent x. Okay, and I think it may be helpful now to rewrite this in terms of cosines and sines. And if I do that, this is the negative cosecant is negative 1 over sine x. And then cotangent is cosine x over sine x. Okay, so let's simplify. We get the limit as x approaches 0 from the right. When I divide by this whole fraction, let's multiply by the reciprocal. That'll give me negative sine squared x over x times cosine x. So now let's try plugging in. If I plug into this, on top I'll get sine squared 0, which is 0. Maybe with a negative sign. Even with a negative sign attached there, it's still 0. And on the bottom I'll get 0 times 1, which is 0. And now this is something I could do L'Hopital's on again. Okay, so we had to do L'Hopital's twice here. But that's okay, we've had to do that before. So we get the limit as x approaches 0 from the right. And I'm just going to associate this negative with the top. If I do that, I'm going to take the derivative of the top, which will be negative 2 sine x. I'm doing chain rule. First I'm dealing with the outside thing, which is the squared. And then times the derivative of the sine. Sine is the inside function. That derivative is cosine. On the bottom I'll have to do product rule. I'll get first times the derivative of the second. So times negative sine x. And then plus the second times the derivative of the first, which is 1. And now let's try plugging in. So if I plug in now, on the top, I will have 0. On the bottom, we will have the first term, the x times negative sine x, that becomes 0. And the cosine x times 1, that becomes 1. I get 0 over 1, which is 0. So I have to be careful. That's not my final answer. Because this whole thing, we started off by saying, okay, this is after we took ln of both sides. This is what ln of y equals. So thus, we know ln of y equals 0. And we want to know what y was. That's what we set our original limit equal to. If I transform this, we get y equals e to the 0, which is 1. And that's my answer. That's what this limit ended up being. This whole thing is just approaching 1. Alrighty, let's do another practice problem. So let's look at number 17. The limit as x approaches 0 from the right of x to the 1 over x. So let me plug in as a first step. I'm gonna be careful as I plug in this time. So I'll write 0 with a little plus sign. That's what I'm plugging into the base. And in the exponent, if I plug in 0 with a little plus sign, I'll get 1 divided by something getting really close to 0, but a little positive. So the exponent is going to be going to infinity. Okay, I want you to do a quick pause, just 1 minute, and see if you can work it out from here. 4, 3, 2, 1. 1 minute pause. See if you can finish it from here. It's going to be really quick once we see the idea. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about a minute. So one thing that I want to notice about this is not an indeterminate form. I have something of the form 0 to the infinity power. That is not indeterminate. Because this essentially means we're having something really close to 0 times itself, times itself, times itself. It's kind of like doing 0 times 0 times 0 times 0 a bunch of times. And there's no ambiguity about what that's getting close to. That is just getting really close to 0. And that's my answer.